course, this is the first topic of Chapter 3, okay, electronic configuration. Okay, and in this topic, we'll figure out the electronic configuration, including noble gas core electronic configuration of the first 20 elements. Okay, let's see this slide. Well, this slide is the part of the periodic table. Why do we want to take a look at this one first? Well, if you take a look at the first 20 elements, okay, if you just put them in one row from hydrogen to calcium, there's nothing special if you take a look at this row. However, if you study the chemical properties of those elements, you realize that lithium, sodium, potassium, those are three elements show the similar properties, chemical properties. And for helium and neon, similar chemical properties. Okay, and so there might be some better ways to organize those elements. And how? Well, here this is the current organizations of those first 22 elements, and you can see that, well, since lithium, sodium, potassium, they have a similar chemical properties, so let's put them in the same group. Okay, beryllium, magnesium, and calcium, they have similar chemical properties, so we put them in the same group. Okay, and same thing here, boron, aluminum, carbon, silicon, and so on. Okay, neon and argon, helium. Okay, so it looks like if we can organize these elements based on their chemical property, we can have a better structure of those elements through the whole periodic table, right? Then the next question is, how do you understand why they have similar chemical properties? In order to answer this question, we do have to identify the electronic configuration of those elements. Okay, similar elements, because they have a similar electronic configuration, they have similar chemical properties. Okay, that's what we will do in this video. Well, this picture is from your textbook. Essentially, this picture shows us the atomic orbitals. Okay, the atomic orbitals. Remember, in chapter 2, we did our analysis and we identified those atomic orbitals based on three quantum numbers: principal quantum number n, okay, angular moment quantum number L, and the magnetic quantum number ML. Okay, and by using those three quantum numbers, we can identify these atomic orbitals. In that chapter and in that video, we use boxes to represent each atomic orbital, right? Here, in order to make things simpler, we use line to represent atomic orbitals, okay? So each line is sort of like the box we had before. Each line represents one atomic orbital. All right. One thing I do want to mention here is, if you take a look at the overall picture, okay, well, it's sort of like we are constructing a upside down hotel. Okay, so these are the hotel rooms. Okay, and each room can be identified by those three quantum numbers. Why do I say that? Let's just use the first one, 1s orbital. Well, 1s orbital, we know that n equals to 1, L equals to 0, ML equals to 0, right? These three quantum numbers define the 1s orbital. How about 2s orbital? Well, that means n equals to 2, L equals to 0, ML equals to 0, right? So this is a 2s orbital. How about the 2p orbitals? Well, same thing. For this 2p orbital, the three quantum number is n equals to 2, L equals to 1, okay, because it's 2p. P represent the value of L as 1. Now, for this particular 2p orbital, ML is negative 1. Okay, and for the middle 2p orbital, n equals to 2, L equals to 1. I'll write the ML down here. So ML equals to 0. For the last 2p orbital, n equals to 2, L equals to 1, ML, okay, equals to negative 1. Okay, so as you notice that each room, each line, and you can go on to identify the 3 quantum numbers for these the orbitals. Okay, so actually, I think this is going to be a good practice for you to review the 3 quantum numbers. Okay, so as you can see that we can use the 3 quantum numbers to define each room. Okay, each room is unique in this case. All right, so this is the quantum numbers. Now let me erase this. Okay. Now the next thing I want to remind you is the energy of those atomic orbitals. Well, from what you can see of on this picture, from bottom to top, energy of those atomic orbitals increase. Okay. Well, I don't know whether you noticed anything strange or not, but if you take a look at this 4 orbitals, 2s and 2p, 3 2p orbitals. If you happen to remember what we did last time when we construct this hotel, and we identified the energy of the atomic orbitals based on the principal quantum number. And remember, the purpose of the principal quantum number is to define the atomic orbital energy, right? So that means if these orbitals have the same principal quantum number 2, they are supposed to have the same energy. In other words, in theory, we should draw the 4 lines on the same level. Okay, on the same level. Okay, so 2s here and 2p here. Okay, because all 4 atomic orbitals have the same principal quantum number 2, they should have the same energy. Okay, and that's what we learned. But in this diagram, you see that the 2p orbitals have higher energy than 2s orbital. Well, what's the reason for this? Well, what I can tell you here is this type of same energy for 2s and the 3 2p orbitals, that can only happen when these orbitals are empty. Okay, but reality is when you have the elements, these elements have multiple electrons. Okay, once you put these electrons on these empty orbitals, then the 2p orbitals will have higher energy than 2s orbital. Okay, so don't let this difference confuse you. Okay, one is for empty orbitals; they are supposed to have same energy. One is for those elements with multiple electrons. Okay, once you have electrons, the energy will be different even if these orbitals have the same principal quantum number n. All right. Now next thing is, let's just go ahead and put the electrons on these hotel rooms. Okay. One thing I haven't mentioned here is, remember we learned actually 4 quantum numbers, and here we only used 3 of them. Now, what's the last one? Remember, the last one is going to be the ms, right? Ms has 2 values, negative half and positive half. Okay. Well, how do we use it? Well, we will talk about ms when we put electrons on those empty orbitals. Before we do that, let's take a look at some guidelines for us to check in our guests' electrons. Those three rules are the guidelines that we need to follow. Okay. Well, the first one is the Pauling exclusion principle. No two electrons can have the same four quantum numbers. Okay. We'll go through them one by one later on when we put the electrons in these empty orbitals. The second one, off-ball principle. Electrons occupy the lowest energy orbitals first. In other words, if you have empty spots at low energy on these atomic orbitals with a lower energy, you cannot put the electrons on the high energy orbitals. Okay. Third one, Hund's rule. When filling degenerate orbitals, electrons fill them singly first with parallel spin. This parallel spin means the same spin quantum number. Okay. When you have these two electrons lined up like this, okay, both of them are pointing up. We say that both of them have positive half spin quantum number. Okay, so that's what this means. Okay, and one thing I do want to mention here is the degenerate. What does degenerate mean? Degenerate means the orbitals have the same energy. Okay, for example, those three 2p orbitals, they are degenerate because they have the same energy. These three 3p orbitals, they are degenerate because they have same energy. Like same thing here for 3 4p orbitals, 5 3d orbitals, 5 4d orbitals. Okay, this is the Hund's rule. Now, let's start from the very beginning. Okay, remember hydrogen. Let's start from element number 1, hydrogen. Well, we know hydrogen has only one electron. So where should we put this electron? According to off-ball principle, electron occupy the lowest energy orbitals first. So you should put this first electron on 1s orbital. Okay, this is for hydrogen. And how do we write the electronic configuration for hydrogen? It's going to be 1s 1. Okay, so this 1s is the atomic orbital, and this 1 is the number of electron on this atomic orbital. Okay, this is a hydrogen. Now the next element would be helium. Okay, helium has 2 electrons. Now when you have 2 electrons, where should the second electron go? Well, from what we have now, for 1s orbital, it has 1 electron already. Okay, and for each atomic orbital, the maximum number of electrons that you can get for one atomic orbital is 2. In other words, 1s orbital can get 1 more electron. Okay. Well, according to off-ball principle, electron occupy the lowest energy orbital first. Okay. So since 1s orbital has has 1 more empty spot. Okay. So the second electron is going to be on the 1s orbital. Okay. So now if you put this second electron on 1s orbital, well, you have 2 options. One, okay, let me write here. One option is you put this electron on 1s orbital with the same direction as the first electron. In other words, those 2 electrons, they are all pointing up. The second option is you put the second electron on 1s orbital with the opposite direction. Which one is right? Well, if you check the quantum number of these 2 electrons with the parallel spin state, then let's just go ahead and identify the 4 quantum numbers for those 2 electrons. For the electron on your left side, n equals to 1, L equals to 0, ML equals to 0. Since it's pointing up, according to what we learned in chapter 2 and also right here, MS should be positive half, right? For the electron on your right side, N1 L equals to 0, ML is 0, okay? MS, it is still positive half, right? Because it's pointing up. Now, if you check Pauli exclusion principle, no two electrons can have the same 4 quantum numbers. Well, if you have this, configuration with 2 electrons in the same 1s orbital, both of them are pointing up, then you will have two sets of same 4 quantum numbers, right? All 4 of them are identical. So this is not right. Okay, we are not supposed to put the second electron on 1s orbital with the same spin direction as the first one. So how about this one? Okay, well, if we do the same thing, let's check the 4 principal quantum number for this configuration. Let me erase this option here. Okay, so I have more space. So for the electron on your left side, N is 1, L is 0, ML is 0, MS is positive half. Now for this electron on your right side, N equals to 1, L equals to 0, ML equals to 0, MS, now since it's pointing down, it's going to be negative half. All right, now if you compare these first 3 quantum numbers, they are the same for those 2 electrons, but the last one is different. So we are not against the Pauli exclusion principle in this case. Okay, so we should take this option. Okay, all right. So this is the, let me erase this part. Okay, so this is how we use the guidelines to help us identify the electronic configuration for hydrogen and helium. Now, next thing is how do we write the electronic configuration for helium? It's going to be 1s2. Okay, 2 represent that you have 2 electrons on the 1s orbital. Now the next one is going to be lithium. Okay, lithium, it has 3 electrons. Now we've already have 2 electrons on the 1s orbital. Okay, now as you can see for the whole diagram, the lowest the empty atomic orbital with the lowest energy is 2s orbital. Okay, so the 30 electrons should go to the 2s orbital. Okay, so in this case, for lithium, electronic configuration would be 1s2 and 2s1. Okay, 2s1. Now the next element would have 4 electrons, beryllium. Okay, Be. Okay, 4 electrons. We've already have 3 electrons. Where should the 4th electron go? Well, like we did for 1s orbital, okay, since the 2s orbital still can get 1 more electron, so the 4th electron should be on the 2s orbital. Again, like 1s orbital, in order to not against the Pauli exclusion principle, the 4th electron should have the opposite spin quantum number ms, okay, which is going to be negative half. All right, so how do we label the electronic configuration for beryllium? It's going to be 1s2, 2s2, okay, because you have 2 electrons on the 2s orbital, okay. Now the next one, boron, it will have 5 electrons, okay. Well, now we have 4 electrons already. The next empty atomic orbital would be one of the 3 2p orbitals, okay. So so the 5th electron should go to one of the 2p orbitals. Well, it doesn't matter. I mean, in theory, it doesn't matter which 2p orbitals you want to have for this 5th electron, because they have the same energy. They are degenerate. Now, however, traditionally, we put the 5th electron on the first 2p orbital. Okay, so for boron, it's going to be it's going to be 1s2, 2s2, and 2p1. Okay, 2p1, that means you have only 1 electron on the 2p orbital. Okay, that's the boron. All right, now the next element would be carbon. Okay, would be carbon. Carbon has 6 electrons. So where should we put the 6th electron on these orbitals? Well, you have 2 options. Let me just copy the 2p orbitals here. 2p and 2p and 2p, so we can compare. Okay. One option is to put the electron, the 6th electron, on the second 2p orbital. Another option is to put the 6th electron on the first 2p orbital with the opposite spin quantum number, -12. Well, let's compare these two. Let's take a look at this. Okay. Well, you probably feel this is not quite right, right? Well, indeed, if you check Hund's rule, when filling degenerate orbitals, electrons fill them singly first with the parallel spin. Well, if you have this, then that's against Hund's rule. Okay, because when you still have empty 2p orbitals, this electron would rather go to this empty room instead of going to this halfly occupied room. Okay, so in other words, this top option is the right configuration. Okay, so it's sort of like you go to a classroom, and in that classroom there is one student there already. So when you get in, you probably will find a empty desk. Instead of approaching the students and, hey, can I share a table with you? Well, of course not, right? So it's sort of like this kind of idea. All right, so let me erase this option. Okay, so the second electron will go to the second 2p orbital. So let's write the electronic configuration for carbon. That's going to be 1s2, 2s2, and 2p2. Okay. All right. And then the next electron is going to be nitrogen. Okay. Nitrogen, it has 7 electrons. Well, according to what we just learned, based on the Hund's rule, since you have one empty 2p orbital, the 7th electron will go to the 2p orbital. Okay. So as you notice, that's 3 electrons. They are going to occupy 3 different 2p orbitals with the same spin quantum number, +12. Okay. Now, for nitrogen, electronic configuration is 1s2, 2s2, and 2p3. Okay. All right. The next element would be oxygen. Okay. We need to put one more electron on this diagram. Okay. Now, of course, since we have 2p orbital with one more empty spot, okay, so the next, the 8th electron for oxygen should be on this 2p orbital, okay, but of course, it has to be the opposite spin quantum number, negative half. Okay, all right, so it's going to be 1s2, 2s2, and 2p4. Okay, now the next element would be fluorine. Fluorine, okay? Fluorine, you get one more electron. So the ninth electron, it will go to this orbital, okay? This one here. Of course, with the opposite spin quantum number, okay? Because they cannot have the same 4 quantum numbers, okay? Now, electronic configuration 1s2, 2s2, and 2p5. Okay. The next element, neon. Okay, neon has 10 electrons. So based on what we have here, we just need to find out where that 10th electron should go. Apparently, it should go to this third 2p orbital. Okay, so for neon, let me write it here. Okay, for neon, it's gonna be 1s2, 2s2, and 2p6. Okay. Now, as you can imagine, if you keep going and you put more and more electrons on these empty orbitals, these electronic configuration would get longer and longer, right? So how do we make it easier for us to write? And it's going to take you time to write those electronic configuration, right? So these are called the full electronic configuration of the elements, okay? So how do we make them simpler and easier, okay? So we need to find a way. Let's use use lithium as an example. Okay. Well, if you compare lithium and helium, helium 1s2, lithium 1s2, 2s1. Okay. So in order to make the electronic configuration of lithium simpler, we can use the helium to represent the 1s2 electrons for lithium. In other words, for lithium, we can write the electronic configuration as helium 2s1. In other words, we use the noble gas helium to represent the 1s2 electrons. Okay? This is a noble gas core electronic configuration. How about beryllium? Well, for beryllium, again, we can use helium to represent the 1s2 electron. So for beryllium, it's going to be helium 2s2. Okay, and for boron, okay, for boron, well, again, like we did for lithium, beryllium, 1s2 still here. Okay, so you can use helium to represent 1s2. So that's going to be helium 2s2, 2p1. Okay, and same thing for carbon. That's going to be helium bracket 2s2, 2p2. And for nitrogen, it's going to be helium 2s2, 2p3. Okay, for oxygen, it's going to be helium 2s2, 2p4. For fluorine, helium 2s2, 2p5. Okay, we can also do this for neon. Okay, because neon, you can use the again helium to represent the 1s2 electron. So for neon, it's going to be helium 2s2, 2p6. Okay, so now we got 4 electronic configurations and noble gas core electronic configuration for the first 10 elements. Okay, one thing we can do, one thing I want to mention here is, okay, when we have the noble gas core electronic configuration, it's easier, it's clear, because it can tells us or it can help us identify the core electrons and valence electrons very easily. What do I mean by that? Well, let's just again use the lithium as an example. Well, as I mentioned, that the helium, this is a noble gas core electronic configuration, right? We use the helium with the brackets to represent the 1s2 electron. So we call this as the core electrons, 1s2 core electrons. And the 1 electron on the 2s orbital, 2s1, as the valence electrons. Let me write it here, okay? Let me use a red color so it's easier. So for this, it's core electron, okay? And for this 1 electron, this is the valence electrons, okay? What's the difference between the two? For core electron, it's not going to be part of the chemical reaction when you use lithium to react with other elements, okay? These 2 electrons always exist, always presents for lithium, okay? But for this 1 electron on the 2s orbital, it will join the chemical reaction if you let lithium react with other things, okay? Most of the time, you are going to lose this 1 electron to become lithium 1 plus. Do you happen to remember how we get the positive ions, cations? Okay, so you lose the electron and then you become a cation, right? So that's why we call it valence electrons, because it's going to be part of the chemical reactions. Okay, let's use fluorine as another example. For fluorine, helium, core electrons. Okay, core electrons. So in other words, this 1s2 electron will not be part of the chemical reactions for fluorine. But for this 7 electrons, they are valence electrons because they will be part of the chemical reactions. Okay, for fluorine, it's going to be the opposite from lithium. For fluorine, most of the time, and I would say nearly all the time, it tends to get one more electron from other species, okay, to become a fluoride. Let me write it here. Okay, fluorine. Most of the time, it will get electrons to become fluoride. Oops, not iron. To become fluoride, because on 2p orbitals, it has only 5, so it tends to get one more electrons to fully occupy the 2p orbitals. Okay. So as you notice, these 7 electrons, they will be part of the chemical reactions. Okay. And for carbon, let's use carbon as an example. Again, this helium, noble gas core electrons, they are not going to be part of the chemical reactions for carbon, but for the 2s2, 2p2 electrons, okay, they are going to be part of the chemical reactions. Okay, some of the chemical reaction for carbon, it will get electrons. For instance, if it gets one more electrons, then it will get the anion. Okay, so but sometimes the carbon will lose the electron, okay, minus electron to become a positive charged ion. Okay, so but no matter what, these 4 valence electrons, they will be part of the reaction. Either they get either you lose the electrons from this the valence electrons, or either you get electron from other species. Okay, it depends on which chemical reaction you are talking about. All right, now I want you to pause this video and figure out the electronic configurations for the next 10 elements. Okay, go ahead and do that. It will probably take you about 10 minutes to do this if you understand these principles. Okay, and identify the full electronic configuration for the next 10 elements and the noble gas core electronic configuration for the next 10 elements. Okay, please go ahead.